Right, grade 11s. Arguably Newton's fourth law. Well, not arguably, but it is his fourth law that we learn about, actually. Beyond school level, I'm not sure if there's another law that exists for Sir Isaac Newton, but I do know that this is the fourth one that is taught here at scholar level, at school level rather. And it's not even counted as his fourth law like Newton's fourth law of motion, as it's all these other laws, 1, 2, and 3, are laws of motion. Okay? Newton's first law, Newton's second law, and Newton's third law, they are all called or categorized as his laws of motion. This one exists entirely independent, as it's Newton's law of universal gravitation. Okay, Newton rather combines the definitions of a force field as well with gravitational field. So, for example, a force field is a region in which an object will experience a force. All right, makes sense. Okay, that's quite intuitive to understand. A force field is a region in which an object will experience a force, hence the term force field. A gravitational field, though, is a region in which any mass will experience a force, which is gravitational in nature. Okay? So, coming back to how he formed his law of universal gravitation, he states that every body, all right, not everybody as in human, but every body, all right, attracts every other body. Every other body in the universe with a force. That is directly proportional it's directly proportional to the product of the masses, all right, the masses of the two bodies, and inversely proportional to the square of the distance between their centers. Alright, a shorter definition that we can also probably write is inversely proportional to the distance squared. Okay, so that's his definition, and his formula goes as follows. F, which is the force of gravitational attraction, measured in newtons as it's still a force, is equal to capital G m1 m2 all over r squared. Okay, where m1 is the mass of one object and m2 is the mass of the other object, and both masses are obviously measured in kilograms, while force is obviously measured in newtons. Okay, r is the distance between the centers of the object, and obviously that is in meters. Okay, and capital G is a gravitational constant, which is equal to about 6,7 times 10 to the power of negative 11 newtons per meter square kilogram squared. Okay, so in some textbooks may give it as different values. I'm just going to check another textbook that I have just to make sure that is the same. as what I am giving it to here from my one source of information, either 6,7, or some textbooks or table of constants may give it to you as, well, it's the same one I think I used when I was at school, okay, as 6,67 times 10 to the negative 11 newtons per meter square per kilogram squared. Which one should I use? Well, it all depends on which one you are given in your formula sheet, in your table of constants when you are writing your exam, or in the question. If the value is given to you, you would need to use that value. For example, if at the end of your question they say take G, the gravitational constant, to be equal to 6,67 times 10 to the negative 11. If they tell you that, then you must use that. You can't use 6,7. Alright? So you must just pay attention to detail. That's all physics is about. Just paying attention to detail. That's all. Alright? Fantastic. So let's have a look at the example here quickly of question 24. So question 24, they don't use Earth or Earth object, but rather we're working with planets here. Alright, so they say two moons of Mars are, I'm going to give this a crack, are Phobos and Deimos. Use the EI here as an A. Deimos, okay? If anybody is watching this later and has found out the correct pronunciation, especially of this one, please let me know. I would appreciate it. They say the mass of Phobos is 1,1 times 10 to the 16 kilograms. The radius of Phobos is 11,1 kilometers. That's the radius. That's not even the diameter. The distance between the centers of Mars and Phobos is 9,377 kilometers, and the mass of Mars is 6,4 times 10 to the 23 kilograms. And they say 24.1, calculate the gravitational force of Mars on Phobos. Okay, so we're working with the planet Mars and one of its moons. Okay, so what do we need to state first? Well, M1 would be Mars, 6,4 times 10 to the 26 kilograms. Okay, M2 would be Phobos, which, if I'm correct, it says 1,1 times 10 to the 16. Sorry, that's a 10 to the 16 kilograms. Okay, I'm making sure it's correct. That's 23 and not 26. I apologize for my error. Okay. They say that R in this case was 9,377 kilometers. What is R again? R is the distance between their centers. They told me that. They were so kind to give it to me. Alright? What else do I need for the question? Now you need to decide what you want to take as your gravitational constant. Okay? What I'm going to do is I'm going to take G to be equal to the one I always used at school. 6,67 times 10 to the power of negative 11. Okay? Newtons per meter squared per kilogram squared. Okay? I'm going to use 6,67. Okay? So, we write down our formula. Switch up the color slightly. F is equal to M1, capital G, M1, M2, all over R squared. Alright, cool. What do we have? 6,67 times 10 to the negative 11, brackets, to make my work look neat. 6,4 times 10 to the 23, brackets, 1,1 times 10 to the 16. Now, if you decided to switch and use 1,1 first, times 10 to 16, and then times 6,4, doesn't matter. It all depended on how you wanted to define your objects. Ultimately, the product of them is still going to happen. R is the distance squared. So I have to square 9,377. Okay? And I punch that in on my calculator, and therefore I'll get the gravitational force. Okay, let's take time just to quickly punch that in on the calculator. You're welcome to do that with me. 6,67 times 10 to the negative 11. 6,4 times 10 to the power 23. 1,1 times 10 to the 16. Almost ran out of space for my calculator. 9,377 all squared. Get a massive number actually of 5,340361558. We round that off now. So 5,34 to 5,34, yes, times 10 to the power of 21 newtons. Okay, and that is going towards Mars. Okay, we'll put that in there, towards Mars. Okay, just out of interest sake, if you decided to use 6,7 and not 6,67, let's just check how our answer would be different. Our answer would be slightly different as to 5,36 would. Oh, I see what's the problem. Okay, what mistake have we made in our solution? Okay, it's a very simple mistake, but can anybody tell me what mistake we've made in our solution? We've actually made two, or rather I've made two. Okay, but I'm not sure if anybody picked it up. The first mistake, R is distance, and it's not measured in kilograms. Okay, it is measured in meters. Second of all, our second mistake was this was a kilometer reading. We have to convert this to meters. So 9,377 kilometers is, of course, a much bigger number. Okay? Much bigger number. Okay? Basically 9,337,000 meters. Alright, so we had to square that number, and that's why our number, this part is still correct, but unfortunately the exponent will change slightly. So let's just go and fix our answer. Alright. Here we go. And a simple fix on the calculator. Just adding in about 3 zeros. And we get about the same answer. And I'm using still 6,7. So it's still 5,34, but it's times 10 now to the 15 newtons towards Mars. Okay. Intentional mistake. Okay. Reason why it's intentional mistake is because that is a common mistake that students make. Okay. Most of the mistakes that happen in these type of questions happens with this variable right here, R. Okay. Students make the common mistake. Remember, I've been tutoring for a long time, so students make the mistake of either not converting from either kilometers to meters, or from millimeters to meters, or from centimeters to meters. They just forget to convert. And the second is they forget to square their distance. Okay? So most often they get the top line correct, they get the numerator right, they get all the numbers correct there, and then they think they're home safe, but actually they've made a huge mistake with R, which is the distance. Please make sure that you do not make the intentional mistake that I made carelessly in your test or exam that is coming up this month. Okay, it's coming up, right, in a couple of weeks. Please do not make that mistake, guys. Please, I beg you. I am crying out. My heart is begging you guys to not make that mistake with R. Please don't. Okay, it will cost you heavily. It will cost you heavy marks. Okay, now This is just an example. But I will give you another question to do a little bit later. Now, this is not the only calculation we do perform underneath Newton's law of universal gravitation. What happens when we're comparing two planets with the Earth? All right? Because we all know what's gravity on Earth, right? Gravity is 9.8 meters per second square on Earth. But gravity is not the same on another planet. Okay? Gravity is not the same on the moon. And the moon is a planet, by the way. Gravity is not the same there. Okay? Moon is not the same. Okay? So Mars is not the same. Okay? Gravity on any other planet is not the same as when it comes to an Earth. So since force of gravitational attraction between an object and the Earth is given by, of course, the formula that we just used now, which was F is equal to M over R all squared. Okay? And I'll tell you what these variables mean, and I'm just going to write G over here. So M0 or MO is the object or the mass of the object. Okay? Of course, where it is, it's on Earth. Okay? And you have ME, which is mass of the Earth. The mass of the Earth is given. Okay? It's a number that is given to you. And RE in this case is radius of the Earth. Okay, and that is also given. Okay, it's given to you. Okay, and since the force, namely the weight of the object, can be calculated, okay, by the mass of the object times the gravity of that object. Okay, but on Earth, obviously, it is the acceleration due to gravity on Earth. Okay. And the mass of the object would obviously also be on Earth. Okay? So we know that these two formulae exist, especially this one, if G, the force of gravity. Okay? Weight. Okay, what I'm trying to say is if we equate these two things together, we'll form a new formula. Alright? A new formula which says that the gravity on Earth, the gravitation on, or acceleration due to gravity on Earth, is equal to the gravitational constant times the mass of the Earth, alright, all over the radius of the Earth squared. What does this mean? From this formula, okay, we can see that G, little g over here, is independent, right, of the mass of the object. It's independent. Okay, that's why it's the subject of the formula. This proves that all objects, whatever their mass, fall at the same rate, which is 9.8 meters per second squared on Earth. So it doesn't matter if it's a big rock or a little rock. It doesn't matter if it's a feather, right, or a brick. They all fall at the same rate, which is, or at the same acceleration, which is 9.8 meters per second squared on Earth. Okay, this formula can now be used to calculate the value of gravity on any planet, as long as the mass and the radius of that planet is known. So this, of course, is for Earth. So now we take that slightly into G of a planet unknown is equal to the gravitational constant, okay, times the mass of that planet divided by the radius of that planet all squared. Okay, and that is a new formula that we have just found. Okay, so E here in this case is Earth. Okay, E, Earth. So the general formula now for any other planet is GP, P for planet. Okay, it's equal to the gravitational constant, G, times the mass of that planet divided by the radius of that planet all squared. Okay, which, if we take an example quickly, example 2. Same example of the Mars and Phobos. Calculate the magnitude of the gravitational acceleration on the surface of Phobos. okay, which is Mars, which is one of Mars's moons. Okay, so we have asked to calculate the gravitational acceleration on the surface of Phobos. So we have G of Phobos, okay, because we name our stuff here, is equal to, of course, the gravitational constant times the mass of Phobos, okay, the mass of the planet, which in this case is a moon called Phobos, okay, all divided by R, or you can use D, all right, R squared, which is our Phobos, all squared, all right, doesn't matter, same thing. Okay, so we're looking for what is the gravity, what is the gravitational acceleration, because it's not 9,8, right, it must be slightly less. Okay, so what do we know? We know that the gravitational acceleration is 6,67 times 10 to the negative 11. Great. What's the mass of Phobos? It was 1,1 times 10 to the negative 11. Or the 16. Sorry, 16. It's a positive number. Good. All over the radius. Right? Now, what did they tell us? They said that the radius of Phobos was 11,1 kilometers. Okay? So 11,1 kilometers would be in meters, because we need to convert that, 11,1 times 10 to the 3. Okay? 11,1 times 10 to the 3. Okay? 1, 2, 3. In scientific notation, all squared. Okay? So what do? We pop this in on our calculator. 6,67 times 10 to the negative 11 times 1,1 times 10 to the 16 all over 11,1 times 10 to the 3 all squared. And we get an answer of 5,95 times, well, 5,95487, so round off to 2 decimal places is 5,95. 5,95 times 10 to the negative 3, and it's gravitational acceleration, so it's meters per second all squared, or meters per second squared. Okay, so what have we just done here using the new formula? We have actually just calculated the gravitational acceleration on the moon of Mars using that formula. Why? Because we knew the mass of the planet that we were considering, which was Phobos. We knew the mass and we knew the radius. We just had to convert it to meters. And we knew the gravitational acceleration because that's given as a constant, plugged it into the formula and found that the gravity or the gravitational acceleration on Mars's moon Phobos is 5,95 times 10 to the negative 3 meters per second squared. 24.3 says, by what factor would the acceleration due to gravity differ on the surface of Deimos? I'm going to go with Deimos. Maybe Deimos sounds a bit more Greeky. Deimos, which has half the radius of Phobos and 1/10 of its mass. Okay, now I've seen these questions ever since I was grade 12, grade 11, grade 12. I've seen these questions, and they are designed to instill fear into the hearts of boys and girls. All right, but not us. Okay, we know exactly what we're doing. Okay, so let me just demonstrate this question to everybody. Okay, whenever you see by what factor, you're asking by how much will the answer change. Okay, it's just a factor. Okay, so the formula stays the same, except that remember, R can be used, D for distance can be used in place of R. You don't have to use R. Okay, so they said that its mass is 1/10. So in the formula you have G is equal to big G, just M for one mass of the planet, and D squared or R squared, doesn't matter. Okay, Now you have that. Take these variables as obviously we know that there's an invisible 1 in front of all these things, right? Algebra doesn't change, okay? Only thing that changes is that we're using G, M, D, and G instead of X, Y, Z, or P, or Q, okay? Which change the variables, but algebra doesn't change, okay? So now they say that the mass now is now changed. So the mass is no longer 1, but rather 1/10 of the mass is Deimos. 1/10 of Phobos is the mass of Deimos. Okay? And they also say that the radius is half that. So half the radius of Phobos is the radius of Deimos. Half. D divided by 2. So we take this and we substitute it in. So G is equal to, well, the gravitational acceleration is equal to the constant multiplied by 110 m over half d all squared. Now I know we were given these values, but we are talking about by what factor. If we ask by what factor, we're not asking to calculate the actual answer. Okay, we're asking the factor. So we can form obviously a calculation at the bottom here. Okay, and we don't really use equal signs, we use the arrow, by the way. So then therefore that means we have 110 m all over, well, a half squared is a quarter d squared. Okay, and g still remains there. Okay, so what do I see here? Here I see I have a, actually I have a sum. I actually have 110 divided by 1 over 4 multiplied by gm over d squared. They match. So this is going to be my factor. So I block this out because now I only need this to determine by what factor. Therefore, that's 110 divided by 1 over 4, which flips into 1 over 10 times 4 over 1, right, which gives me a final answer of 2.5. Okay, 2.5. 2 divided by 5, or 2/5. So my factor is 2/5. So basically, if I take 2/5 times the gravitational acceleration that I got in my first answer, it'll tell me if it's going to increase or decrease. But basically, the gravitational acceleration will decrease by 2/5. If I got a whole number, if I got 2 or if I got 5, then we know the factor or the gravitational acceleration will increase. But if I get a fraction like this, then I know my final answer is that the gravitational acceleration of Deimos will decrease by 2.5. Okay, so Deimos is actually 2, not 2.5, 2 over 5. Sorry, I'm mixing my words here. So Deimos, which is the gravitational acceleration of Deimos, differs by 2/5. Okay, by what factor would the acceleration due to gravity differ? So this answer, if you times it by 2 over 5, you'll actually get what is the gravitational acceleration on Deimos, which is less or smaller than on Phobos. And that does conclude my session for today. Thank you, grade 11s, for joining me on Newton's universal law of gravitation. And please stay tuned for the next topic. We have actually put Newton's laws to bed. So please stay tuned for the next video where we start our next topic.